So today we'll cover JFETs. We're going to wrap it up and maybe a few minutes extra left in the end. We'll look at the first slide of MOSFETs. Okay. JFETs also the experiment in the lab next week. That's also another reason why I wanted to cover JFETs earlier than MOSFETs. So let's bring up the last notebook. Okay. I believe we had stopped here for both classes. So brief recap. JFET is a N-channel device. You have a semiconductor of N-type material, and we implant P-type material in there. That creates a gap between the two P-type materials, meaning there's a channel between the two P-type materials. The two P-type materials are connected together, and we form a terminal we term as the gate. The two ends of the channel are labeled as drain and source. And because it's an N-type material, there is a abundance of negatively charged electrons that are available to conduct charge. If you apply a voltage between the drain and the source, meaning across the channel, you'd expect electrons to move and current flow as a result, right? Then we have the gate. Well, if you apply a negative voltage at the gate, we saw that the P and N junctions are reverse bias. And because they are reverse bias, the depletion region increases. And because the depletion region increases, the channel starts to narrow. Eventually, at one point, both the depletion regions end up meeting together. The channel pinches off, and we say the device is turned off. The level of VGS, where the channel pinches off, is known as the pinch off voltage, VP. Okay, so this is what we looked at so far. So in this case, in this slide, VDS was not applied. VDS was equal to 0. Okay, so the drain voltage is 0, and VGS was increasingly negative. That resulted in the device being turned off. Now let's look at the case where VGS, the gate, is 0, and we apply an increasingly positive voltage at the drain, which will result in current flow. Okay. So here we have, right now, ignore that VGS is less than 0. Okay. Ignore that. The case is that VGS is equal to 0 volts and VDS is greater than or equal to 0. So VDS is increasing. So if VGS is 0, we have two PN junctions. The channel width, so the channel gap is already present. If we apply a positive voltage at the drain, what happens to the electrons? Positive voltage, electrons. Physics. Opposite charges attract, right? So the electrons are attracted to the positive charge at the drain. Hence, there's a movement of charge carriers, hence a flow of current. So current starts to flow. That current is labeled as the drain to source current, IDS. IDS. Okay, so we have current flow if we apply a positive voltage at the drain with respect to the source. So VDS is greater than 0, meaning a positive voltage attracts electrons, hence current flow. But at the same time, due to the construction of the JFET, this is what happens. You have a N channel or N-type material that is connected, that is positively biased. So what happens at the PN junction? It's right there. What happens to the PN junction? Think back to chapter 2 and 3. Or actually, don't even think that far back. What happened in the previous slide? Reverse bias PN junction, depletion region increases. And because the depletion region increases, at some point, again, pinch off is going to occur. Let's take 10 seconds. VGS is equal to 0. You apply a positive voltage, so current starts flowing through the device. But the other effect of the positive voltage at VDS is that the P and N junctions are reverse bias. Hence, the same effect takes place that we saw in the previous slide. The depletion regions are still increasing in size, and at some point, they will end up meeting. The reason the depletion region is larger at the drain end is because the drain to source voltage is higher at the drain, right? Voltage is higher at the drain, and hence the depletion region is larger at the drain end. And so we have kind of a slope in the channel right here. But eventual result is the same. So if I was to draw a characteristic of VDS versus ID, this is what I would expect to see. When you first apply current, you get a linear line. And then the channel just about pinches off. And because it pinches off, it levels off. Okay. What would you expect to happen to the current when the channel pinches off? That's what we would expect to happen, absolutely. It should go to 0. However, what was noticed was that the depletion region, of course, does not, when it meets, does not quite pinch off the channel. So the term is kind of a misnomer. There is a small gap in there, and not just a gap. Electrons can also go through the depletion region and towards the drain and just move out. And so current flows through that gap. It reaches a saturation level. And the level does not drop. Okay, it does not increase, it does not drop. So even though the channel meets right here, even though the channel meets right here, it's not quite pinched off. There is a current of very high density. There's a current of very high density that is still flowing through the device. Okay, and it's flowing through the gap. And hence, it does not drop to 0. It actually remains at a constant level. And that is the effect of the externally applied electric field. And this level of ID is known as IDSS. Is the value of the current IDS with a short circuit between the gate and the source. So this S right here stands for short circuited or short circuit, gate to source. Meaning VGS is equal to 0 volts. So the value of IDS, the drain to source current, when VGS is equal to 0, is referred to as IDSS. That is by design. It depends on the manufacturing process. So every spec sheet that you look up for JFETs will have a value of IDSS that is specified. Okay, let's take a 10-second pause. Let me know if you have any questions. Yes. Yes. No, it's not a parasitic current. So can you rephrase your question so I can understand it better? You said the point of the gate was to? Yes, so it does allow the current to flow through the JFET. But remember, this device in normal equilibrium state, we state it as it's on. We must apply a negative voltage to control and turn it off. It's a depletion mode device. And when we say on, the on comes from the fact that the channel is open. The channel is normally open. We don't have to apply an external field to create a channel. So I believe I did state it here. Let me see. Let's go back. I think I did state it somewhere. Yeah. So normal is on. The normal is on refers to the fact that when the device is manufactured, the channel is open. It already has electrons or carriers present. Since we are talking about N-channel JFETs, it's electrons. If it's P-channel, it's holes. But again, it's important for students to understand that when we say the device is normally on, means that the channel is open. It's manufactured open. For other devices like MOSFETs and other devices, a channel must be created by applying a voltage. Okay. So this is a depletion mode device because we need to apply a negative voltage or a voltage at the gate to turn it off. So we are controlling it with the gate, but just the fact that the channel is normally open and applying a gate voltage, we're going to turn it off. And so the control will come here. So the gate actually is controlling. Right now, we're looking at the maximum value. Okay, so VGS is 0. In the previous slide, we saw what happens when VDS was 0. Now we are looking at the case where VGS is 0. And when VGS is 0, the value of the current that you obtain is the maximum current that can flow through the JFET. Okay, so it's kind of the reverse, not the reverse, but you're looking back. You're not looking forward in that sense, if that makes sense. This is the maximum current that can flow through the JFET. Okay, but I want students to understand this right here. If we don't apply any VGS, channel is normally open, as shown here, right? Channel is normally open. Now, if you apply a positive VDS, meaning positive voltage at the drain, current starts to flow. But at the same time, the depletion region is also increasing. And the depletion region increases. At one point, it meets, which is right here. So there is a pinch off that is occurring. There's a pinch off that is occurring even when VGS is 0. Two separate cases. Okay, and this is a very common point of confusion. So I want to ensure that each and every one of you understand this. In the previous case, VDS was 0. You're simply applying a negative voltage at VGS. No current was flowing to the device except for reverse saturation current. And the channel pinches off. That is VP, pinch off voltage, right? VGS negative, pinches off, that is VP. Now VGS is 0 and you increase the VDS, drain to source voltage, you have current flow, but at the same time, the channel starts to close because of VDS, not because of VGS. That's a different thing. And the point where the channel just meets for the first time due to this VDS is also referred to as pinch off, and that voltage is known as VDSP. The pinch off voltage, pinch off value of VDS. So it's known as VDSP. Okay, VDSP. All right, let's take a pause. Think over that. Let me know if you have any questions. And again, it's two different effects. First one, VDS is 0. Second one, VGS is equal to 0. Any questions? Are you all with me or lost in the clouds? Does the operation make sense? Yes. Sure. Okay. So recap. Here, VDS is equal to 0 volts. No current is flowing. Meaning IDS is equal to 0, 0 amps. Okay. And VGS is increased. And when increased, we mean increasingly negative. So increasingly negative voltage is applied and the channel pinches off. When the channel pinches off, we refer to that voltage as VP, pinch off voltage. So the only current that flows through the JFET there would be like reverse current, reverse saturation current, very small. And in the next scenario here, we have VGS is equal to 0 volts. And now we apply increasing voltage at VDS. That is the main two terminals of this device. In a diode, we have two terminals, we have current flow through the diode, but we don't have a third terminal to control that flow inside the device. In transistors, whether it's BJTs or FETs or MOSFETs, we have a third terminal. We call that third terminal as the gate. And that gate controls the flow of current through the device. So in a diode, we have current flow between the anode and cathode. In FETs, we have current flow between drain and the source. That is the primary current, the output current. And that is controlled by the gate voltage. So in the first case, VDS was 0. We were just determining what is the pinch off voltage for the device. The second, then this is more important, where VGS is 0 and VDS is increased. So we have current flow through the device. But a resulting phenomena is that with increasing VDS, there's still pinch off that is occurring. But this pinch off is not the same as the previous one. In this pinch off, there is still a current flow. There is still a small gap. A current of high density is still flowing through the device between the drain and the source. And that max current, that current is the maximum value, and it's known as IDSS. And it depends on the manufacturing process. Does that help? Nothing flows through. Exactly, yes. So now if we put both of these together, what do you think would happen? Meaning we apply a positive voltage at VDS, and at the same time we apply a negative voltage at the gate. What happens when you apply a negative voltage at the gate? The gate width narrows, right? Channel is narrowing, width decreases. So by default, even before we apply VDS, channel width is narrowed, and then thus the maximum current that can flow for any value of VDS is now reduced. So we have linear region, but the level of current is now reduced. So for increasingly negative voltage, this is VGS 0. This is, well, let's just put negative 1 volt. We just keep things simple. We obtain a set of curves, and with increasing negative gate voltage, that current is reduced. And eventually, VGS crosses the pinch off voltage VP, where it doesn't matter what VDS you apply, because it's pinched off due to VGS, current is always 0 or at very, very, very low value, like the saturation current. And we say the device is turned off or cut off. Now, this is VDS, by the way, and this is IDS. I stated that. And for every value of VGS that is applied, there is a VDSP. This is known as the linear region or the triode region of operation. And this is known as the pinch-off region of operation. And right at the bottom is the cutoff region. So as I was saying, we have to think of it as backwards. Normally, we would say the device is cut off, but you apply a voltage and then it allows current to flow through, right? But this is a depletion mode device, meaning the channel is always on. So you apply a voltage to actually reduce the current. We are still controlling the current flow via the gate, but we have to apply a negative voltage to actually reduce it all the way to 0. Does that make sense now? Okay. And when we say the device is normally on, we are referring to the fact that the channel is open. When you buy a JFET from the manufacturer, it's always on. Okay, questions? Any questions? I have a better graph on the next page. Right here. So this is the maximum IDSS where VGS is equal to 0. This is the pinch-off region. And this is the linear region or the triode region. And we'll talk about the linearity in just a bit. So far, so good. This is the output characteristics. Output is always the drain source voltage VDS versus IDS, or IDS is a function of VDS. And then the transfer characteristic. How is the input being transferred to the output? Well, the input is VGS because VGS is controlling, right? And the output is the drain source current, IDS. So this is the transfer characteristic. And you take the max current value and bring it to the left. For every value of VGS, you will have a corresponding value of ID. And you get this plot. This is also one of the questions on the pre-lab for next week. And that's the answer. Plot the transfer characteristic curve for the JFET. So this is the answer. All right, questions? Any questions? Does it all make sense? Maybe, maybe not. Can you come up here and explain? Okay, so let's talk about the linearity. Let's go back to the construction of the device. Right here. So this is an N-channel JFET because the starting material is N-type. Okay, N-type material means a lot of free electrons available. For a P-type JFET or a PJFET, we would have a lot of holes available. So now when we implant dopant impurities in semiconductors, it allows, depending on the dopant, it creates resistance in that material. Okay, the material has some resistivity. That resistivity has now changed, okay, because of the implants. And because the channel is conducting electrons, meaning it's conducting current flow, it inherently has resistance. Resistance is normally given by rho L or A. And because the channel has some resistance, we refer to that as the channel resistance RCH. RCH. Okay. And the equation for RCH is the resistivity of the channel, the length of the channel, and the cross-sectional area. Okay, cross-sectional area. The length of the channel, of course, is this. That's the length. The width is the separation between the two P junctions, I mean the two P-type material. And so that is shown right here. W and L. And then the cross-sectional area is given by the depth of the implant into the silicon material. So we have a semiconductor, right? The semiconductor, you're going to implant either N-type or P-type material. When you implant it, it goes deep into the, well, it goes into the surface. It does not go too deep, it's shallow. So for a 500 micron wafer, it's probably just a few microns from the top. When it goes in there, the implant is buried inside. And so there is a shallow layer of the channel that is a few microns deep. So the depth of the implant is basically the thickness, and that gives us the cross-sectional area. Does that make sense? The depth of the implant into the substrate, into the wafer, gives us the thickness of the channel, and the thickness can be used to determine the cross-sectional area of the channel. And so that can be given by CH T times W, where W is the width of the channel and T is the into the substrate. Okay, questions? No questions? It's going to be on the quiz on Monday. All right, let's look at a example problem of biasing the JFET. So we have a JFET here, creating a circuit with 3 resistors, drain resistor of 2000 ohms, source resistance of 1 kilo ohm, and gate resistance of 680. Okay, we want to keep the current as small as possible. One of the properties of the JFET is that it has high input impedance. So the gate current is very negligible. And for most analyses, we assume that the gate current is equal to 0. Okay. So in this case, we have a JFET, we have a voltage source VDD, and we ask to find the Q point, the operating point of this JFET. Remember, operating point is the constraint placed on the device by the external circuit and the external source. right? So we want to find the Q point. And the Q point in this case would be the drain to source voltage, VDS, and the drain current, ID. So we are asked to find VDS, ID, and VGS. Okay, VGS. Okay, all right, let's begin. So for a diode, it was straightforward. We had two terminals. We applied KVL, KCL, any circuit analysis technique that would work. We'll do the same thing here. But for transistors, what we do is we break up the circuit into two parts. We break it up into the input and the output side. Okay. So for this JFETs, input side is the gate source, output side is the drain source. And source is the common terminal between the two. So in the input side, we have three voltages. We have the voltage drop across RG, the voltage drop across RS, and the gate to source voltage VGS, which is one of the things we need to find. So we'll begin by applying KVL at the input loop. We apply KVL at the input loop, and we see the current is flowing in this direction. So it's plus minus, plus minus. And so we can write VRG plus VGS plus VRS is equal to 0. Now this becomes IGRG plus VGS plus ISRS is equal to 0. Now, remember what I was saying about the gate current. For most analyses, we would assume the gate current IG to be equal to 0. So in the circuit, what do you see? You have three terminals, so we have three currents: the drain current, the source current, and the gate current. Okay, current comes from the top, flows through here. If you apply KCL, the sum of the three currents should be equal to 0. And if the gate current is 0, we can state the drain current and the source current are exactly the same. And so we can write ID is equal to ID IS, which also makes sense because we just saw in the previous slide, electrons are flowing from the source to the drain, currents flowing from drain to source, and it's exactly the same current. Gate current is negligible. So IS is equal to ID. So we can plug those in here, and we can write VGS is minus ID times RS. IG is 0, so that term is eliminated. VGS is then simply IS times RS. We take it on the other side, we get minus IS times RS, and we substitute ID in place of IS. So now what do we do? It's two unknowns in this case, right? VGS and ID. But ID has an equation. ID has a standard expression like the diode equation, and we can use that equation to determine the value for ID. So ID can be given by IDSS times 1 minus VGS over VP square. Okay, VGS over VP square. And we can plug that into this equation, and we obtain VGS is equal to minus IDSS 1 minus VGS over VP times RS. Because IDSS and VP values are given to us, RS is known to us, we can simply plug those values in here, and we can obtain an expression with just one unknown, that is VGS. And so let's go ahead and do that. VGS is equal to minus 5 milliamps, so 0.005 times 1 minus VGS over minus 5 whole square times 1,000. We solve this, and we can obtain, let's see, minus 5 divided by 25, and here it would be 5 plus VGS square. So that gives me 5 VGS is equal to 25 plus 10 VGS plus VGS square. Take everything on the other side, and we can write an expression that looks like this: VGS square plus 10 VGS plus 15. Sorry, not 15. This is 15. 15 VGS plus 25 is equal to 0. So we obtain a quadratic equation. Plug this into your calculator, calculate the roots, and you obtain VGS is equal to minus 1.91 volts, or VGS is equal to minus, what do I have, 13.1 volt. All right, write it down, think over this, and let me know what do you think is the correct value for VGS. Take a look at all the information that is given to us. Why? Yep, absolutely. VP is given to us as minus 5 volts. 13 is larger than 5. It would be in cutoff region. That is the correct answer. And so VGS, since VP is minus 5 volts, VGS is equal to minus 1.9 volts. 1.9. Okay. Okay. And we can find ID from this value. We can write ID is equal to IS, to 1.9 volts divided by 1,000. This is 1.91 milliamp. And then we can find, how much time do we have left? We have 10 minutes. So Let's apply KVL at the output loop. Because we need to find VDS. And so we can now write an expression. We have 4 voltages. VDD is being split across the drain resistance, the source resistance, and then of course we have VDS. So we have drain resistance VRD, we have VDS, and we have VRS. Therefore, VDD is equal to IDRD plus VDS plus IS times RS. IS and ID are the same. We want to take VDS on the other side because that's the unknown quantity. So we get VDD minus ID times RD plus RS. ID and IS are the same, so we take it outside, combine the two resistors, and we can get value for VDS as 12 minus 0.00191 times 3000. That gives us VDS is 6.27 volts. 6.27. All right, write it down. Let me know if you have any questions. Questions? Oh, sorry. Yeah, VDD is the standard nomenclature for the voltage that is applied on the drain side. And so it's VDD. On the gate side, we say it's VGG. This is something also you'll see in the lab. So the lab has the same circuit, except we'll apply both voltages and obtain a set of curves. So this is the reason I wanted to complete the GFET before we begin lab next week. Okay. So we apply negative voltage at the gate, then we apply positive voltages from 0 to 5, 6, 7, 10 volts, and you obtain a set of curves for the GFETs. This is also the reason, yes. It's also the reason why we have to be careful not to apply positive voltage at the gate. So if you apply a positive voltage, you will inadvertently end up blowing out our JFETs. So we have to be very careful. Yes. That's a standard expression, yes. Like a diode equation, this is the equation for ID. And IDSS, again, depends on the manufacturing process. IDSS can also be given by Kn over 2 times Vp square. This is all dependent on the device manufacturing process. Okay, Kn is known as the transconductance factor. Transconductance factor. And so it depends on the manufacturing process. So when you buy a standard JFET off the market, the spec sheet will list the values of IDSS as well as the pinch-off voltage, Vp. Okay. All right, 5 minutes left. All right, any questions? All good? Yeah. Okay, let's look at MOSFETs. What the heck are MOSFETs? The name is, well, that's quite a mouthful, metal oxide semiconductor field effect transistors. Yeah, that's where the name comes from. So MOS comes from the fact that we use metal, oxide, and semiconductor in the construction of this device. So there's a semiconductor layer right here. You have a oxide layer right here. That oxide is silicon dioxide. So SiO2, silicon dioxide. It is also the reason why silicon is by far the most popular material of choice for microchips. Okay, because it's very easy to create an oxide for silicon, and that oxide has very excellent thermal as well as electrical insulating properties. It's an excellent thermal insulator and it's an excellent electrical insulator. So in this case, you have a semiconductor material, you put an oxide layer on top, and then that oxide layer isolates, electrically isolates the semiconductor and the gate, which is made from a metal material that is on top of the oxide. Hence the name, metal oxide and semiconductor, MOS. The example shown here, the channel does not exist. It has to be created by applying a voltage. Okay, so it does not exist. Okay. In this illustration, we have a P-type substrate and we have N-type implants in there. So it creates an N-type channel or an N channel for short. And when you have an N-channel MOSFET, we refer to it as an NMOS. NMOS device. If it's an N-type substrate, we have P-type implants in there. We create a P-type channel, and we call those devices PMOS, as P channels. What do you think it's called if it's both NMOS devices and PMOS devices? Any wild guesses? That's a good guess. You all are probably familiar with the term, though. It's called complementary MOS or CMOS. Complementary because one of the easiest and the first structures built from N and PMOS transistors was an inverter gate. You connect the NMOS and a PMOS transistor back, well, not back to back, quite back to back, kind of like in series, and you can create an inverter gate out of those two transistors. And that is one of the easiest or the most basic of building blocks for our logic circuits. Anyway, once they were able to create a fabrication process for both NMOS and PMOS on the same devices, it took off in a big way. Almost all computer chips that we use nowadays are based on the CMOS fabrication process. Every device that we use, every microchip that we use is based on the CMOS. It has both NMOS and PMOS transistors on there. Okay, and that's where the name comes from. So this is where I stopped in the previous section. So this is where I'm going to stop here too. Just announcement, quiz as usual on Monday. It will be based on the material we covered this week. So basically JFETs, maybe a problem, but mostly short answer questions, concept based. There'll be a short homework assignment and a reading assignment based on what we covered this week. So I'll post that as soon as I get back in my office within the next hour or so. And then again, quiz based on that material on Monday. Okay. It probably won't be as long as 20 minutes, maybe 15 minutes or so. And then we'll try and wrap up MOSFETs on Monday and then get into the bulk of our remaining material, which is the BJTs. Most important topic. Okay, so I'll bid you all a good weekend and I'll see you all on Monday.